Today we'll talk about waves. Basically, we see waves phenomena everywhere. We hear sound, that's an effect of the wave. You go to the seaside, you see wave of the sea water coming towards you. You drop something into the water, you see the pattern of the wave fronts traveling out, so that's waves. You receive your phone call, that's because of electromagnetic radio wave. You see light, that's because of the electromagnetic wave also, okay, in the visible region. So we also have things like microwave. We also have the earthquake that create waves across the structure of the earth. Okay, so those are phenomena of the waves. Okay, so in this topic we are going to look at some basic properties of wave, on how they are generated, on some of the properties of them, for example like frequency, wavelength, period and all that. Okay, of course you have studied this before, but A-level syllabus will require you to revisit all this also. Okay, and then there are more difficult concepts like phase difference, intensity. Okay, so let's start. First of all, let's talk about wave pulse. How to create a wave pulse and what is that? Picture here shows you that if you have a string that you tie to somewhere, or even you don't fix it also can, then you hold one of the end and then you start vibrating it. Okay, you move the hand up and down, then you would be able to see one wave pulse. This is the wave pulse. It's traveling. Okay, so that's the wave pulse. So here I use the PhET simulation to try to create a wave pulse. Alright, so I move this thing up and down, and then you can see that there's a wave pulse created, and it travels from the point of the movement that I created just now. Okay, so what happens if I continuously move this thing up and down? Then let's see. So continuous wave pulse will travel in such. So together they are called the waves instead of just wave pulse. So they are continuous wave pulses that join together. All right. So now let's look at how this kind of wave behave. So what you see just now is that they actually travel away from the point of disturbance. So the thing that I'm holding now and oscillating it is called the disturbance, point of disturbance. And you can see if I want to do that, I mean really if I want to do that using a physical one, I have to use some energy to move this. So that energy will go into the energy of this thing oscillating or vibrating, and therefore the waves will transfer this energy out of this point where I give it energy. So it's always transferring out energy from it. All right, once you got that kind of vibration and it sends out the energy from the point of the disturbance, we call that kind of wave as progressive wave. So the wave progress as they move on. So like what I said just now, it is a disturbance. Okay, from the point of disturbance, it will move through a certain distance with a certain velocity, and it transfer energy from the point of disturbance. However, you must notice that the particles on the string just now, they are actually not traveling with the wave. Their motion is just like up and down. So I'm going to show you one more time in a slow motion of those kind of motion just now, but they are not moving together with the waves away far and far from the point of disturbance. So let's get back to that. I'm going to the continuous wave pulse one more time, and this time around you look at those green particles on this string. Okay, you look at how those green particles move. Yeah, maybe just focus on one of them. All right, so I'm going to bring out a ruler so that it will be easier for reference. So the first one here we got it at 1 cm, the other one is at 2.5 cm. So I start to move it now. So I created a wave that travels out of from this point. Okay, now I'm going to move it bigger so that you can see how the green particles at 1 cm move. Alright, so basically it will just move up and down. So in order to generate a more continuous one, because I need to keep on moving in such a way, so now I give you an oscillator. Okay, then at least now you can see a bit clearer. So this 1 cm, the particle at 1 cm here, it just move up and down. It never travel together with the wave, and so do other points along the wave. Alright, so energy transfer away. You see that the profile is moving, the peak is moving towards the right hand side. Alright, this animation on the other hand will show you how the movement of left and right, because just now in the slide it mentioned left and right. Okay, so now I'm going to use this speaker to generate a wave across the air. So let's see. Okay, I press on the green button, and then I'm going to slow it down so that we can focus on the red color dots along the line. Okay, along the line, a horizontal line, you can see those particles, the red color particles, they are moving left and right. So in order to further illustrate that, I'm going to use this thing, okay, to measure the pressure there. Okay, so pressure itself, you can actually also look at it in terms of the displacement of the particle, because it vary in a similar manner. So you can see when I point to the red color particles in the air, it actually oscillate left to the right. It is depicted as an up and down motion in this measuring device. Okay, they go up and down and such. So this is a common example when we go to near a pond or near a lake, that we throw something into the water, and then we can see the rings of the wave fronts spreading out from the point of disturbance. Okay, so we have this term called the peak and trough. So peak basically is the highest point on the wave, and trough is the lowest point on the wave. Okay, from the top view, as in bird eye view on the right hand side here, you can see that those rings, they actually become bigger and bigger, and then they spread out. Okay, so I'm also going to demonstrate that using this simulation. So now this is like water, and then I start to drop water droplets into the water. Alright, so the black color is like a trough, and the blue one is like a peak. So peak usually we call wave fronts. Okay, we usually see the wave fronts traveling out in such. Okay, this is a bird eye view. Then we can look at the side view. So side view, we can also see the peak and the trough even clearer. Okay, in this case that you can see the displacement actually reducing, because anyway that's usual, because they will actually become smaller as they travel further due to the dissipation of the energy to the surrounding. Okay, so we come back to the slide here to describe more on the movement of the particles on a wave. So this diagram or graph here shows you some label particles O, P, Q, R, S. So if we were to label, then let's say this is the first second, okay, and this is the second. So they are like a snapshot of this wave as it travel. Third second, you can see that they are moving at a different. They are at a different position at first second, second second, and third second. So together synchronously, they are creating this profile that you can see this peak, right? It's like it has moved towards the Q position, and then it moved towards the R position as the time goes by. Okay, so By the way, it is because of the particle moving up and down that they transfer the energy in such that you can see the profile traveling. That's why this type of motion is called, this type of waves is called progressive waves. All right. So here's the more challenging part, because you are supposed to know how exactly at this moment, I'm showing you an example here, at this moment the particles are moving. Where is the direction of motion of these particles moving if you are given a snapshot like this? So direction of wave is clearly indicated. It is, so let's say there's a point of disturbance somewhere here. Okay, so it sent out the wave and the energy is being transferred to the right. So these particles, they are moving up and down. The thing is that we need to know whether they are moving up or moving down, or they are actually temporarily stationary at that moment. So if you view the animation, of course it will be easy, because you can see their position from time after time. But let's say you just have this snapshot, just one snapshot like this. How are we going to describe them? Okay, so here's a technique that you must master every time you are asked about this kind of question. So first of all, we draw a wave that is one moment later, one short moment later. Where is this wave? So if the energy is traveling, or the wave is propagating to the right, of course the red color wave profile is what is going to shift to, correct? So let's try to think through this first. Okay, you need to understand how it works first. I'm trying to bring the color, but it doesn't seem to be able to, but never mind. So I'm going to use a dotted line to shows you one moment before. Where is it? Okay, one moment before, where would it be? So of course it will be somewhere before the solid black color line. There's one moment before, one short moment before. Okay, so I'm drawing this. All right, so the dot color is before, this is now, and this is after. Okay, we are going to use these three terms, before, now, and after. So now let's look at the particle O. Particle O just now is here, now is here, and later is going to be here. So which means that we should know that, I mean, we can simulate that using these three fixed position in time, that it is going to move up. I mean, it is moving up at this moment. Okay, so using this method, we can clearly and confidently say that the motion of this particle O is moving up at this moment. So similarly, let's look at point P just for another example. Just now it's here, now it's here, and later is here. So where would it move? I guess you can easily now making the summary. So of course it will be moving down. So O moving up and P moving down. All right, Q and R is slightly different because they are at the peak of this wave. Okay, they are at the peak, they are at the maximum displacement. So just now Q is here, and then it moved to here now. Later it's going to move down again. So which means that it's at a turning point. So when it's at a turning point, we describe that Q is momentarily stationary. Momentarily stationary. So it stopped for a while there before, I mean, at the change of direction. And so do R. R actually is also momentarily stationary. Okay, its speed is 0. So speed is 0 at Q and R. Speed is non-zero at P and O. Okay. Right now, let's look at this property called wavelength. Wavelength is the length of the wave. Okay, so this might sound a bit unclear, but later we're going to define that, what is exactly wavelength. So let's say you have a snapshot of this wave that is moving. Later we're going to do that on the simulation. So we take a picture, and then it's here. Okay, so we see the crest, we see the trough, and you can see the label there. The wavelength is in between the two crests. So what we define is that distance between any point and the next identical point of the wave is called the wavelength. So it is showing one example, then I'm going to show you another example. So let's say this point and then this point here. Okay, so this is an identical point because at this point they are zero displacement and they are moving up. Okay, both of them are moving up at this point. Okay, so we call that identical point. So that's also one wavelength, and any other pair that you are able to find. And the symbol given to wavelength is called lambda. So now we look at the simulation. How do we get that? Alright, we'll use back this wave created by the droplet of water. So first of all, I'm going to freeze the screen. Okay, so this is the wave created by this droplet of water, and then I'm going to use the meter here, measuring tape here, to measure. So let's say I put it here, and then I measure from here to this identical point. Okay, so I see that it's about 2.7 cm. So this is the wavelength of this wave. So similarly, if I put for any other identical point, then it should measure the same, is 2.7 cm. That's the wavelength created by this. Okay, so if let's say I'm looking at here, then I should measure the wave fronts. Okay, because we can't take the identical point, so we just roughly take in between the wavefront, so it's 2.7 cm. All right, so next thing we will look at further three more quantities related to a wave. That's called amplitude, period, and frequency. Okay, so this is not a snapshot, yeah, this is different. The axis here is time. Later we're going to use the simulation to figure this out also, and we can see that the displacement, maximum displacement from the equilibrium point, is called the amplitude. Okay, now the other position we call them displacement. The highest displacement we call the amplitude, and between the two identical points here, now it's not called wavelength anymore, now it's called period, because really we are looking at a different thing. We are looking at the position of one particle, just one particle. Okay, later I use the simulation to explain to you again. Plotted against the time. That means we focus at one motion of one particle on the wave, and then we plot the graph. Okay, so let's define those quantity first. Amplitude is called the maximum displacement from equilibrium position. Period is called the time taken for one complete oscillation. Okay, one complete oscillation. It moved up, it moved down. So let's say this particle here, I mean this point here, at this point in the moment, it moved down. Okay, then after that it go further down, then after that it come up, and then it reaches the same point where we started talking about it. Then it is one complete oscillation, come back to the same position of the oscillation, then we call it the one oscillation, and time taken is called the period. Frequency is number of oscillations per unit time. So you can see that I actually cut off the word complete, because that word is not necessary. Okay, it can be like 2.5 oscillation, it can be like 3.2 oscillation, so it depends. So number of oscillations per unit time, we don't have to state that in integer, so it can be in a decimal number. Okay, so now we go to the simulation. Alright, I bring out this device that measure the water level, and I focus its screen, I focus its measuring instrument at one of the point or one of the position along the wave. Then I started moving it, and then you can see that on this meter here, it shows you up and down. Okay, so that's recording the position at the particle there at different time, and then plotted it on the monitor. Okay, so it's not a snapshot, it's how this particle at this position move. Alright, so then if I freeze this, and then we can now measure the time. Okay, so we can now measure the time. So how do we measure the time? Of course we need to do some conversion. So this peak to this peak, okay, is one period. It come back to this same point. Okay, that's one period here. Alright, then we can use the you see you can see that here it says that 1 second for one box. So the one that we have measured just now is like one big box plus maybe half a box there, so that's like 1.5 second, and that's the period of this. And we actually don't need this because it's already having a scale there. So this period here is like 1.5 second. Okay, so that's how we measure that.